Big data, artificial intelligence, and machine learning. These terms are everywhere in contemporary public life and in academic research, now even in the humanities. These developments and technologies are changing many industries and fields. Some of these disruptions have improved our lives immeasurably. Others have caused injury, produced misrepresentations, and re-embedded prior biases under the guise of a corrective mechanical objectivity for now discredited human subjectivity. Today, I want to bring together the resources of humanities scholarship and computational methodology to provide a critique of machine learning for text classification. I'll provide a few examples of text classification, but my primary object of critique is a deeply flawed model produced by two literary scholars who claim that their approach can accurately determine whether a novel manuscript will become a bestseller. My book, Critical Digital Humanities, The Search for Methodology, is a metacritical account of the field of computational literary studies and a manifesto. It provides readers with tools to critique even many complex machine learning tasks by breaking down the assumptions and procedures of computational scholarship into steps or stages, what we call a workflow. I position my book within the ongoing discussion of reading methods. I understand the discussion of computational literary studies as made possible by the plurality of reading methods in the present, and sharing some of the features of post-critique and the surface reading. I write of one important difference between computational literary studies and other humanistic reading methods that lays out the stakes of my talk today. The alluring promises of the use of large-scale computational methods for the humanities have enabled many literary critics to assert that it is now possible to deploy entirely new ways of reading, and that these approaches have obsoleted the slow, interpretive, and critical work associated with most humanities scholarship. These computational tools, however, are not transparent, nor are they value-free. Computational methods bring with them an entire set of assumptions and concepts derived from the empirical sciences that may or may not be antithetical to the goals of humanities research, including, just to name a few, falsifiability, sampling, statistical significance, and the notion of semantic meaning embedded in many of these tools. The incorporation of digital methods into humanities research requires more methodological awareness and self-critique. Let's begin by talking about an example from everyday life. How we encounter new cultural objects, most importantly, how we're exposed to new books. We are moving from expert-provided recommendations and top-down dissemination of opinions to potentially a more democratic system by which we locate and consume culture that has been authorized by the truism that we are all entitled to our opinions. This is both good and bad. We could find new books outside traditional channels, but we're unable to tell if the marketplace is rigged. For example, in the case of Amazon's own efforts in publishing under their own imprint. When we are greeted with seemingly appropriate recommendations, we assume the algorithm knows us better than we know ourselves, or that it knows something crucially about the texts themselves, but it does not. The era of machine-driven recommendations, think of Amazon and Netflix, comes complete with its own ideology. Big data, as the combination of data and algorithms and the logic of correlationism, has been offered as the solution to a range of social issues, from policing to determining eligibility for insurance. Big data boosters join the chorus of those opposed to critique by declaring the end of theory. Chris Anderson, while editor of Wired magazine in 2008, wrote, "This is a world where massive amounts of data and applied mathematics replace every other tool that might be brought to bear. Out with every theory of human behavior, from linguistics to sociology. Forget taxonomy, ontology, and psychology. Who knows why people do what they do? The point is they do it, and we can track and measure it with unprecedented fidelity. With enough data, the numbers speak for themselves." I hope to demonstrate how wrong the statement is, especially when concerning literary texts. Before we move on too far, I should define two big data era keywords. I'm using algorithms loosely to describe classification algorithms that determine the membership of objects into categories or classes. Algorithms are recipes and always formed in response to predetermined goals. These goals are the condition of possibility for their operations. Features are what classification algorithms use to determine class membership. Features must be comparable across objects. Otherwise, we have no basis for comparison. If we're interested in genre, for example, every book must have a genre, and the set needs to be internally coherent. Thus, Gothic must mean the same for every text in which this would be a possibility. Now let's turn to sources, turn to possible sources of features for objects that should be of special interest to us. I've defined 3 kinds of features here that are all quite different. First, metadata, as information about data, can give us pre-existing features that are well known and usually well determined. These are cover level features, as it were. Object relations describe the social network around a book. This really has nothing to do with the content of the book as such, but the people who like it or purchased it. This is the primary ideological mechanism by which machine learning convinces us that it has learned something about us. Finally, the text as data means going between the covers and turning a text into a set of features, typically word or phrase counts. Quickly, we can apply that same logic to music as well. Metadata would be your old experience with something like iTunes, scrolling or browsing by genre or artist. Object relations is how the new streaming services like Spotify function. Music as data is more difficult, but sometimes used by streaming services as well. You liked this, you might like this as well. Both have the same musical signature. But what exactly is that signature? That is the problem and our focus. We've now defined 2 key terms and examined possible sources of features. How do we know which features are most meaningful? Well, we attach labels to those features and test our classification algorithms. We split our labeled data into a training and testing data set. Both have known classifications attached to them. Say we're interested in genre, we label everything with a genre. The testing and training data sets need to be similar. This is a very important assumption. We've just temporarily removed, for the purposes of testing, the genre labels from the testing data to generate sample classifications to later test and determine the accuracy of our classifier. The training data provides the algorithm with key features for determining class membership. Now let's return to those features. What happens when we convert a text into data? Here we see a paragraph from a text, Lucy Larcom's A New England Girlhood, and the resulting data set of features. This is a vector representing some of the information in that original paragraph of text. We've deformed it into a document term matrix, a list of word repetitions. And we'll note that we've lost much of the form of the paragraph. We've lost capitalization, we've lost punctuation, we've lost word order. We can use more complicated features if we have them. Here, for example, is the part of speech tags automatically generated from the HathiTrust archive for a sample section of A New England Girlhood. We'll note here the preservation of punctuation in the rendering of this text. Despite the existence of these tagged words with part of speech, the most basic and commonly used method remains simply counting words and phrases. Now, how are the features turned into the basis of classification? Here's a classic example. Eugenicist Ronald A. Fisher generated this iris flower data set in 1936. This has been the foundational data set for most machine learning applications. He has defined 4 features, sepal width and length, petal width and length, that enable him to classify samples of iris flowers into these 3 classes. This data set works well because although there is some variation within each of the 3 classes, there's greater variation between the 3 classes. The K nearest neighbor classification algorithm, the algorithm I devoted a whole chapter of my book to, is 97.4% accurate, and when it's used on a set of testing data that's been split off from the training data provided by Fisher. Now let's turn to text. Can we build a periodization classifier? The big move here is to move from the flower measurements, right, the sepal width, the petal width, length and width, right, to imagining our word and phrase counts as those features, just like the prior ones. We built a multi-dimensional matrix of word frequencies, and we use this as the basis of comparison. These features enable us to determine which words or phrases are more highly correlated with particular classes of text. In American literature, we've traditionally held to a major division between the antebellum and postbellum period. This has been under increasing pressure recently for many good reasons. We can ask if, based on the count of words in phrases alone, it's possible to tell which period, antebellum or postbellum, a text might belong to. We can classify or label all of the text and then hold some out from our testing from the algorithm. It's trained on known samples, and like the 3 classification problem for the iris flowers, and then we check on the performance of the algorithm on these test objects. So here are some of the words and phrases that are more associated with the postbellum rather than the antebellum period. And this is for slave narratives from the North American Slave Narrative Archive, the primary object that I return to again and again in my book. Some of these differences reflect changes in language, and others changes in the context and reception of the texts. These words produce something that I think of as the leftover. The leftovers of the classification task turns out to be the most useful component for literary scholars. I sometimes refer to this leftover as the slag from text mining, but it, along with the numerical weights learned by the algorithm, should really be the main object of analysis for humanists. The slag, when we are mining text in literature, especially, are not sortable in the way in which data work in the natural and social sciences. Theoretically inclined humanists understand that these words are ambiguous signifiers. Polysemy, irony, repetition, allegory, metaphor, these are all too easily collapsed into the document term matrix. Sometimes even junk data becomes meaningful in terms of an explanation produced by an algorithm. Here, for example, we're looking at an archive of 18th century printed lyric work. We have short text classified as ballads, odes, prayers, and songs. This is a version of what we just saw with the antebellum, postbellum classifier, although we'll note a few things. There's the presence of the long S that's rendered as similar here in this representation as an F. It's a correctly encoded textual feature, but frequently it is not. Printed language differences, older English characters and Latin are some of our best features for determining genre. But what to make of PDF in page and PDF page? Well, it turns out that the ballads were much more likely to include spurious information from the digitization procedure. These would be noise, not signal, but they're important to the algorithm in determining if we're looking at a ballad. Self-validating methods, appropriately cybernetic, work recursively, take up and amplify their own nonsense. This method does appear to have some predictive power when using this existing set of texts. This is only by fate of an accident. If we were to add new lyrical works or correct our errors, everything would change. If we add even another class of objects, we'll introduce changes that alter the results and the important features. These models, in short, are quite brittle. Armed with this understanding, I now want to spend the remainder of my time discussing the bestseller code. Jody Archer, a former acquisitions editor working in Publish, and a literary scholar trained at Stanford, together with Matthew Jockers, an English professor and digital humanist, published the bestseller code, The Anatomy of a Blockbuster Novel, in 2016. Their book attempts to provide a quantitative rationale for the question of what makes a book a bestseller. They write, traditionally it is believed that there are certain skills a novelist needs to master in order to win readers: a sense of plot, compelling characters, more than basic competence with grammar. Writers with big fan bases have mastered more: an eye for the human condition, the twists and turns of plausibility, that rare but appropriate use of the semicolon. Archer and Jockers are telling us that they have discovered the feature set that will determine if a novel will become a bestseller or not. I'm cranky about this particular example of computational work in the humanities for several reasons. The bestseller is not a natural set. The class of iris flowers are named, defined, and shaped by humans, of course. Flowers are a cultural data set. But when we take samples of these, we assume that our samples belong to a sortable, natural distribution of these flowers. Bestsellers is not a static category, but one that changes with the times. When one examines these books, you're not examining literature as such as much as the market. The market is complicated. An approach based on the content of selected features from text rather than market forces and features, even say race and gender of the author, is rigidly formalist. By this, I mean to say that it assumes a continuity of form within the class that is stronger than other features. This model is much like the prior circulated lists of topics that could be potential bestsellers, those that might be used by acquisition folks and readers for agents, than a real objective data-driven analysis of the manuscript. Using the exact methods I have just reviewed, Archer and Jockers built a model that contained two classes, bestseller and not bestseller. They collected words and phrase counts from a series of books labeled bestseller and not best. They tried to capture measurements that would enable them to extract what they wanted to present as the equivalent of a DNA sequence for each book in the bestseller list. With these building blocks, they claimed to be able to produce an anatomy of the class bestseller. They tuned the feature list using both training and testing data until they produced a reduced set of words and phrases and a dubious proxy for plot movement derived from the average value of sentiment scored words that would make accurate predictions on their testing data. Text can be rendered data, but the link between classes and features is not the same as DNA. Archer and Jockers make a mistake in applying the natural science model of the iris flowers to understanding bestsellers. Their book explains some of the results of their model, but does not provide access to their data or even a clear explanation of their methods. It engages in a mystification. This is registered in the fetish object of 2,799 features. This mystification was a strategic decision as they were interested in using the bestseller code as a platform to launch a consultancy. Archer Jockers will take your book manuscript and extract the 2,799 features that they have determined make up the bestseller code and tell you if they correlate with the features they have identified as belonging to the class bestseller. Archer Jockers provides on their website, which is where this image comes from, glossy graphics that they use to tell would-be authors, our former students, to create more characters like 50 Shades of Grey's Christian Grey. But we do not know how they determine the words, spoken by whom, and in what sequence and number make up the category of industrious, active, and likely in control, or happy, active, and inclined towards laughter that they say characterize Grey. Computational literary studies, of course, does not function exactly like Archer Jockers, but because these models are so brittle, they must disclose the evidence with which they make their claims. If this evidence cannot be made interpretable, then it cannot be made part of any academic argument. Archer Jockers and the bestseller code is a deeply cynical and exploitative method and project that seeks to turn profit from publishing dreams, but it's hardly the worst example of what I call big data obfuscation. I'd like to conclude by extending this critique to other applications of machine learning. Statistics and big data are increasingly used as aids in decision making. Despite claims otherwise, prior information, biases, and decisions are always embedded in these models. Simple two-class classification, gay, straight, recidivism risk, no risk, you, not you, is unreliable and does not model the world as it exists. The use of black boxes or proprietary algorithms, systems, and extracted features make it impossible to contest the decisions made about us. For Antoinette Rouvroy and Bernard Stiegler, we've entered into a mode of what they term algorithmic governmentality, in which there can be no redress for misclassification because there's no longer targeting, but instead profiling of our statistical doubles based on correlations of these unknown features. Researchers, corporations, and governments are increasingly turning to opaque algorithms, unsupervised learning, and complexity with the justification that these are better methods. These so-called better yet obscure methods are patent medicine at best. At worst, they are what Cathy O'Neill in her recent book helpfully terms weapons of math destruction.